hypothesis testing with larger samples. Example 7, a light bulb manufacturer tested n equal 50 of its light bulbs and found x equals 0 defective light bulbs. Does this sample provide sufficient evidence that the manufacturer meets the industry standard of fewer than 10% defective? So again, we'll make a chart diagram showing the relationship between the sample and the population. So this sample of 50 larger light bulbs was from a larger population of, let's say, millions of light bulbs. So in a sample of n equal 50 bulbs, the proportion of defectives p hat be 0 over 50, or 0 divided by 50 is just 0. So this is taken from the larger population. In population of millions of bulbs, a portion of defectives P, and we don't know what that is. Put a question mark there. And we want to compare it to the industry standard. So if company does not meet the industry standard, company does not meet the industry standard, then the proportion of defectives would be P0, which would be 0.1. Company needs to have fewer than 0.1 defectives. Okay, so let's use the language of hypothesis testing. With 95% confidence or 5% doubt, we want to test H naught, P equal 0.1, company does not meet the standard, versus HA, P is less than 0.1, company does meet the standard. They want fewer than 10% defective. So this is our null hypothesis, and this is our alternative hypothesis. Okay, so let's check whether n times p0 is at least 5, n times 1 minus p0 is at least 5. So so 50 times 0.1, that's 5, and that's going to be a yes. Some books might say no, some books might want strictly greater than 5, but we'll be using if anything 5 or more, we're going to say meets our standard. And then 50 times 1 minus 0.1 is 0.9, 0.9 is 45, greater than or equal to 5, and that's a yes. So that means that we can use the z table as a shortcut to approximate the likelihood of getting a result this extreme if h naught is true. Okay, so n times p0, should have a p0 here. Okay, so the next step is to compute the mean and standard deviation of x if h naught is true. So mu times p0, so that's mu is equal to n times p0, which is 50, times 0.1, which is 5. So on the average, if h naught is true, we can expect 5 defectives. And then the standard deviation square root of n times p0 times 1 minus p0. So 50 times 0.1, and 1 minus 0.1 is 0.9. And then we can put this in the calculator. Let's go. Second square root 50 times 0.1 times 0.9 equals, I get 2.12 something. 1320344. And I'm going to store this in memory, so I don't have to retype it in the calculator. Okay. Okay, so now we can compute the z-score. And it's the same formula we were working with earlier in the semester. Score minus the mean divided by the standard deviation. Okay, so it's going to be, we had 0 defectives, 0 minus, and the mean, if h not true, would be 5 defectives out of 50. And then divide by standard deviation at 2.2.131320344. Okay, so we can do on the calculator 0 minus 5 and then push equals, because a calculator doesn't know about a division bar that goes all the way across. They only know the short division symbol. And then divide by, and I'll recall this from memory, oops. Oh, okay, yeah, let's do this again. 0 minus 5 equals, divide by second recall. I don't know why. I don't know why. I thought I had this in memory. Okay. No, I didn't store this in memory. Second square root 50 times 0.1 times. Okay. Okay, I get approximately 2.36, negative 2.36. Okay, so this is a left-tailed test, and if we use the empirical rule, or Triola's range rule of thumb, any z-score less than negative 2 is going to be unusual. A more precise rule would be any z-score less than negative 1.645. And our z-score is negative 2.36, so that's an unusual z-score, and so that means we would reject H naught. Reject H naught with 95% confidence, and conclude company meets the standard. The 10% standard. We can also combine steps 2, 3, and 4 and do that all in one step. Z is equal to x times n times p0 divided by the square root of n times p0 times 1 minus p0. So that's going to be 50. No, 0, x is 0. 0 minus 50 times 0.1 divided by square root 50 times 0.1, and 1 minus 0.1 is 0.9. And again, the calculator doesn't know about the long division bar in terms of order of operations. So we want to put in the numerator and then push equals after we put in the numerator. So 0 minus 50 times 0.1 equals, then divide by second square root 50 times 0.1 times 0.9. And again we get negative 2.36. Okay, so some of the homework exercises might want you to take it a step further and look this number up in the z-table. And for a left-tailed test, we want to keep the same sign as our test statistic. We don't need to change the sign because we're using a left-tailed table and we're with a left-tailed test. So we want the probability of z being less than negative 2.36. And we go to row negative 2.3, column 6 of the z-table. That'll give us our p-value. So it's negative 2.3 and column 6. Our p-value is 0.0091. So the p-value. So if we look at our table here, it's between 0.001 and 0.01, so that would be strong evidence. Sample provides strong evidence that the company meets the standard. Even though we met the criteria for using the z-table, the shortcut, the binomial probabilities will be more accurate. Usually it's going to be it would be very time consuming to compute the binomial probabilities. It's a lot easier to look up the z-table, but in this case the tree there's only one path in the tree where there were no defectives, so just that one path. It's going to be 0.9 to the 50th power, which is 0.0052, so that's a more accurate p-value. Our p-value is 0.0091 using the z-table to get the approximate p-value, but the more exact, the more precise p-value here would be 0.0052. But in either case, it provides strong evidence. The sample provides strong evidence that the company meets the standard of having fewer than 10% defective. And that concludes this presentation.